think the only one is for question number 3. Remember that when you have count less than equal to 1, the minimum count is going to be 1. I mean, it never shows you count 0 because that means there should be nothing else around. So, so if, having count less than equal to 1 is equivalent to saying having count equal to 1. Okay, so so then I'm going to continue with the functional dependencies that I was doing in the last class. So at the end of last class, we were looking at functional dependencies, and I went through a few examples. So I'm just going to continue with FTs today. So there are a few functional dependency rules. So we have and these rules are make it easier when we do problems later, because eventually we have to get around to normalizing tables. So in order to do that, you have to know, you have to start with functional dependencies. So the first rule is the splitting rule for functional dependencies. So let's say you're given a functional dependency, and I'm going to break it up. So let's say we have attributes A1, A2, to so on, AN, functionally determines the attributes B1, B2 to BM. So it's like saying first name, last name functionally determines social security number, address, and so on. So that's really what this is. So saying something like this is equivalent to saying A1, A2 is equal to B1, B2, and so on. To BM. So first name, last name functionally determines social security number, first name, last name functionally determines address, and so on. So this is valid. But if you write down A1 or AI, let's say, AI determines B1, B2, so on to BM, or you say that AI determines, say, BJ. So if you say first name determines address or something like that, that is not necessarily valid. Okay, so this is kind of intuitive, and so I'll just give the example as the one I just said, first name, social security number, and let's say address. So if you have something like this, you can write it down as first name, last name determines SSN, first name, last name determines address. But if you wrote down first name determines SSN, that is not necessarily correct. Maybe that doesn't hold true. You might have two people with the same name, first name. So that is the splitting rule of functional dependencies. It's like I said, it's you can understand that intuitively. The second rule is the combining rule of functional dependencies. So So this one again, if you were given, I mean, again, this one's also kind of pretty trivial. If you are given something like first name, last name determines social security number, first name, last name determines address. So, essentially what this is saying is you look at some place and you find that there are two different tables, first name, last name, social security number, and then there's a different table that says first name, last name, and address. And you find that, why have two tables? Why not combine it into one table? So, so this is like saying we have R1, which has first name, and then you have R2. So the combining rule just states that combine into a single table. Which has first name, last name, SSN, and address. So on the left side, you can't break up, but on the right side, you should actually combine. If you have the same things on the right, so that's really what it is, combining rule of FDs. And so then the next one, rule number 3. So these are, again, if you have any questions, just jump in. I just think these are kind of straightforward. The third one has to do with the key. So this is called the key super key. So now I don't know if I ever spoke about super key, but now we have a super key rule of FDs. So what is a key? I mean, I kind of informally spoken about keys before, so I just want to formally define it. So A1, A2, and so on to AN is a key for a relation R, which has A1, A2, and so on to AN, and then attributes B1, B2, and so on to BM. If 1, A1, A2, and so on to AN functionally determines B1, B2, and so on to BM. And the second rule is that A1, A2 to AN is the smallest subset. You can't have, you can't have A1, A2 determining B1, B2, and BN. So this is saying no proper subset of A1, A2, and so on to AN is a FD of R. So this is the smallest, it's a minimal set. You can't have anything smaller than this functionally determined B1, B2, and Bn. And so, and sometimes you might find that you have multiple keys. So if you have more than one key, then you can pick one key as a primary key. So if more than one key, pick one key as the primary, and the other one will become the candidate key. So all the others are candidate keys. So again, the social security one is a good example. So again, so suppose we have SSN, first name, last name. So we have this relation R, say address, phone, and DNO. Okay, and suppose you have SSN determines address, phone, DNO, and you also have first name, last name determines SSN. So in this case, both of them, they determine all the other attributes. So both of them are keys. SSN is a key. So we have SSN is a key. Also, first name, last name is a key. So both of these are keys. And they are minimal because because first name by itself does not functionally determine everything else, nor does last name by itself functionally determine. So these are both minimal sets. So both of them are keys. So then it's up to you which one to pick up as a primary key, and the other keys are all candidate keys. So are there any questions? Okay, so this is the key. So now the next thing is, what is the super key that I spoke about out here? So we have a key. So what is the super key? So a super key is just the key with other attributes added onto it. So it's something that's not minimal. So that's really what a super key is. So super key is not minimal. So for example, I have social security number up there. So if I said social security number and let's say address determines, after all, that will determine everything else too. You have first name, last name, phone, DNO. So SSN and address, that's a super key. So it's like first name, last name, and phone, that's a super key. So a super key is just, you have, it's not minimal. So you can have, there are extra attributes added onto it. That's all that it means. So this is a super key. So that's a super key. If I wrote down, like I said, first name, last name, phone, that'll also determine everything else on the right side. So we have, so these are both super keys. So that's all that a super key is. So a formal definition of a super key is just a set of attributes that contains the key. That's a super key. So we had that A1, A2, A3 to AN going to B1. B2, BM. So in this A1, A2, A3, and so on to AN. So if you have B1, B2, that's a super key. Or even if you go all the way to BM, it doesn't matter. So, so in a super key, also I want to have defined two other terms. So we have super key. So all of these, the ones that are, all of these are called prime attributes. So, so these are all prime attributes, and these are called the non-prime attributes. Okay, so just remember them because the prime attributes and non-prime attributes will crop up when we talk about normal forms. I'm going to do a few examples, and you can see, hopefully that will help you. Even if you have questions right now, these examples should help you clear up any doubts that you have. So let's say we have a relation R and we have attributes A, B, C, D. And okay, so whenever I underline something, that means that is a primary key. So, so in this case, A has been underlined. So A is a primary key, and A determines the keys B, C, and D. So A out here is prime, and B, C, D are all non-prime attributes. And a super key would be anything you have A inside is a super key. So AB is a super key, ABC is a super key, ABCD, AD. So anything with A in it is a super key. Okay, so yeah, and then yeah, and I'll do some more examples later. I think we did 3 rules so far. Yes, so I want to do a 4th rule before I jump down to. So the 4th rule is the transitive rule of functional dependencies. So that, just like the name suggests, what it says is that if A determines B and B determines C, then that'll imply that A determines C. Okay, so so for example, if you have this particular table where you're given, so what the implications of the rule is, let's say we have this particular table with 3 attributes A, B, and C, and you're given that A determines B and B determines C. So B2, C2, A3, B1, A4, B2. So suppose you have a table with some entries that are missing, but you are told that that these rules hold, then you can make out. So you know that if A3 determines B1 and B1, so let me just put it on. So we have B1 determines C1 out here, and you're told that A determines B. So since A determines B and B determines C, out here we know it's going to be C1. And similarly for the next one, A4, you're given that A4 goes to B2, but B2 goes to C2, so you can fill C2 out here. So if you have missing data when you are, going through a database and there's some the data that are missing, but you know that these functional dependencies hold, then you can put down the missing data. Okay, so so it's a good rule from that viewpoint. Okay, so I'm going to do, so this were the 4 rules. I'm going to do a couple of examples that. Okay, so let's say we have this table with 4 attributes, A, B, C, and D. And the tables, so you have A1, B1, C1, D1. I just want to make sure. A1, B2, C1, D1, 2, B3, C2, D1, and A2, B4, C3, D1. So what I want you to find out are the key and the functional dependencies. The question is find functional dependencies and find the key. So I want you to just look at this table and find that out. So what is the key for this table? Someone, anyone?
Looks like B would be.
Yes.
Key.
That's, yeah, actually this one's, because whatever is the key, it has to be something which is unique on every row. So as you can see, B is the only one that's unique on every row. All the others have some repetition. So B is the only one that's unique. So the key part is really easy. The key is B. And so once you have a key, so you know that definitely when that's the key, you do know that there is this functional dependency that has to hold, and that's a key. Is there any other functional dependency in here besides this?
Would C implies A be one?
C, let's see, C, yeah, because D, one thing, the D part, if you look at D is the same everywhere. So everything has to imply D anyway. So that's one functional dependency you can say, is that C determines D, and so does A determine D. So that you know. So let's see, does C determine, so which one did you say? C determine what else?
A.
C1, A1, C1, A1, C2. Yes, so C does determine A. So you can actually just write it as 1, actually. You can just write it as C determines AD, you can write it. So, or DA, whichever one. Is there anything else in here? Yeah, I think that's all there is that I can see right now. So, so the main thing is, you know, you can, if you just wrote it as C determines AD, that was fine too. Okay, so yeah, so if you have any tables, you have to look through it and figure out. So a lot of times when you, you know, so there are 2 ways of finding functional dependencies. One is actually looking through the data. And when you have very large tables, remember, you have to have programs that look through the data. We can look at something as small as this and try to figure out, but we make mistakes too. Even with such a small table, it's easy to make mistakes. So the human brain is not good at searching data and finding out sometimes, but the computer is really good at searching through data and finding functional dependencies. But what we are good at is talking to people in a corporation and asking them, because, for example, very directly in UNH, you know that the your UNH ID will determine everything else. You know, if anyone has access to your UNH ID, they can find everything else about you, if they have permissions, of course, because all these databases have access permissions anyway. So the next question is that instead of looking at a table, so right now we were looking at tables. Suppose, so look at this next one. Problem is you're given a set of functional dependencies. So this example is how to find key given a relation R with all attributes. And the functional dependencies. So let's just take an example, and I'll take the one that we keep using. So suppose you're given the following functional dependencies. Social security number determines manager DNO. DNO determines DName and manager. Then we have PNO, project number determines project name, project location, and DNO. And then finally, we have the work one. We have SSN, PNO determines the number of hours you work on the table. So we have one big table R. So you can just think of table R has having all the attributes: SSN, name, manager, DNO, DName, PNO, PName, P location, and then I think I just have to move this a bit to the, and then finally we have ours. Okay, so we have this big table with all the attributes, and we want to find the key for this this big table R. So I mean, because we have been looking at this example for so long without doing anything beyond this, if we only were given, so what can anyone guess what is the key for this big table R? Given that we've been doing in the company database for a while.
Probably like SSN.
Okay, SSN. Okay, that's a good, very good guess, because we've been doing all this for a while, and SSN seems to really figure out everywhere. So let's take a look and see, is that true? Would SSN do? So, so there is a way to, this is called closure of attributes. So there is a very, and there's an algorithm you can just say to find out what is the key for this big table. So this algorithm, I mean, we can call it closure of attributes. So this is called closure attributes. Okay, so since you said SSN, let's start with SSN. Okay, so we'll look at SSN and we'll say, okay, from if you are given SSN, what are the other attributes you can find out by looking at SSN? So it's like, it's almost like saying that in UNH, if I'm given your student ID number, what are all the things that I can find out given your student ID number? So it's some similar to that. So it's called closure of attributes. So it's saying SSN plus, and then on the right side, we put everything else. So you put SSN itself out there. Okay, so you have to start with SSN. So the next thing you do is you look and see, okay, SSN is on the left out here. What are the things that are on the right of this functional dependency? So typically you pick something that's on the left of a functional dependency. So we have SSN already out here. So then I look, so I know that given SSN, I can immediately find the name, the manager, and the D number. So all of this follows from this part, from the very first functional dependency. So I got this from FD1. Okay. Now, but the thing, so now I have these, now I have in the set, now I have SSN, name, manager, and D number. So then I look at this part and I look, what do any of these attributes appear on the left of any of these functional dependencies? And if you look on FD2, we have DNO determines DName and manager. So we say, oh, okay, so I have DNO out here and DNO determines DName and manager. And I already have manager out here. Okay, so that's already there, but I don't have DName. So I can add DName out here. So that's what you do next is that you come down here and you add DName. So that would be, so what I did is I looked at this one and that's how I got this one. So this is from FD2. Okay, so is there anything else I can get? Now I have, does anything else on the set appear on the left-hand side out here? And there's nothing else. So when I do closure of attributes out here, if I have only SSN, I cannot get the entire table. So this table is not equal to this table. So therefore, SSN by itself is not a key. Okay, so did anyone understand this part as to why SSN is not a key? Okay, so the next thing I will look at is, let me look, okay, so SSN is not a key, and you can know by what I just did right now that, there's no way that D number would be a key, because from D number, we are, because we already have D number out here and we couldn't get the key from that. So there's no point in looking at D number. So let's look at PNO instead. So you take a step, I don't see any point in picking up DNO, it's just a waste of time. So I'm going to look at PNO now. So let's look at PNO plus and see what will come in on the left. So if you look at P number, okay, so you find that you have, so you have P number, and then you have P name, P location, and you have D number. So that is, so if I look at this one, I get all of these come out. Okay, so that's FD3. Okay, but again, from DNO, I can get DName. I did that earlier. So we have from DNO, we can bring DName. And that's FD2. So, oh, have I missed out something? Oh, and from D number, I forgot. There's one more thing. I missed something else. I forgot that if I look out here, you also have manager. So I can bring in manager too. I didn't see that, sorry. Okay, so we have manager too. Okay, but we still don't have the entire table because we don't have the attributes. We don't have the following attributes. We don't have name. We have manager. We don't have R. So these are the two attributes that are not there. Okay, so using so far with these three, FD1, FD2, FD3, we have not been able to get all the attributes. So now next, let's look at SSN and P number together. Okay, so we have so there we have SSN, P number, and we have R's, but so we have the so that's FT4, but we also can bring everything else in now because we're going to have from the P, we have P name. Oh, I should have. So going up, we have P name, P location, and DNO. So this is FD3 comes in because we already have P number, and P number determines all of these. And then we have from social security number, we have name, and then we have manager, and then we have D name. Okay, so and that's FD1. So if you use SSN and P number together, you can get all the attributes. So the key for so how to find the key? So the whole question here was how to find the key given a relation R. So we have to find this key. So in this case, the key is SSN. So key of R. So this is the key, and this is the, you can't go any smaller than this. That is the key for this particular table. So in this case, I would underline SSN and P number. So these two together are the key for this table. So is there any questions? Did you understand what I just did? Okay, so let's take a look at some examples. Even if you haven't understood, hopefully these next examples will help you understand. Okay, so instead of calling this an example, I'll call this a question. Next one. Okay. Okay, so let's say we're given this table R, A, B, C, D, E, and you have to find the key. And you're given the following functional dependencies. You're given that D determines B, AB determines C, and AE determines D. So I would like you to find the key for this particular table. Okay, did anyone find the key?
looks like AE would be the key, I think.
Yeah, actually you're right. You know, AE is the key. So again, out here, this is, if you do D plus, all you can get are D and B. So that's definitely not the key. If you do AB plus, you get A, B, and C. There's nothing else you can get from it. On the other hand, if you do AE plus, you'll get A, E. I mean, I write the uppercase E because my lowercase e sometimes looks like a C. So A, E, D. But then D determines B. So that brings in the B. And then AB determines C. So you get the entire, you know, because AE will determine D, then this D determines B comes from here. And then AB determines C comes from here. So you get the entire set. Okay, so.
I have a quick question. What's the plus on, what does the plus stand for?
Oh, it's just saying closure from D. What are the other attributes you can add on to the table?
Oh, okay.
That's all it means. Yeah.
I get it.
It's called the closure property. So, so let's look at this next example and see if you can try to. So you have, again, attributes from A to F, and you're given the following functional dependencies. You're given AB determines C, BC determines AD, D determines E, and CF determines B. So I would like you, so there are multiple keys. So I want you to find the keys. So find the keys for this table. And when you find one, don't stop. There are two different keys. So they're candidate keys in this case. Because if you do AB, if you look at AB, you are not going to get everything. So you get A, B, C, D, and E. So you can't get the F in there. If you get B, C plus, you get B, C, A, D, E. The problem is that, you know, one of the things, I just want to give you a simple trick is that, you know, whatever you do, whichever key you're going to find must have an F in there. because if you look on the right-hand side, F does not appear on the right-hand side at anywhere. So if you have an attribute that never appears on the right-hand side of a functional dependency, that means F has to be in the key. So anything without an F in there, you're not going to get a key anyway. So that's a clue, by the way. So let's anyway look at CF. So we have C, F, and B. Then from BC, you get AD. So then you have A, B, C, D. So I haven't got E yet. And from D, you get E, right? So definitely CF plus is a key, but did anyone find the second key, the candidate key?
I guess it would be ABF, right?
Yes, whatever you find, like I said, you must have F in there. And so if you look at ABF also, you can find that it's a key. So let's look at ABF plus. Will give you A, B, F of comes in my default. So AB you'll get C, BC will give you D, and then D gives you E. So ABF is also a key. So we have two candidate keys. So we have okay, so, and these are minimal keys because if you remove the F from either one, you're not going to get F only appears on the left. So F has to be in any key and it's a minimal key. If you remove BF by itself is not a key, AF by itself is not a key. You can check and see, that's something you must check and see. So you do need A, B, and F together to get the key because in order to generate. So if you, let's see, if you wrote something like, so if you wrote BCF, so with BCF also you'll get the entire thing on the right. But BCF is a super key because CF is a key, right? So BCF is just a super key. It's not a key. Because it's not minimal. Did everyone understand? So far, have you understood what's going on? So I do want to mention that, the textbook is actually pretty good for many things, but some of the stuff about functional dependencies and all, I would say the normal form is not that well explained in the textbook. So it's because they jump to normal forms directly without really going through some of the stuff earlier. So what I'm doing right now are things that are not really mentioned in the book so much. And it's kind of important to understand this part before you start doing normal forms. So, so if you don't have any questions, I would say that's it for today's lecture. So there will be a quiz in the next class on Wednesday morning. Yeah. So the quiz will be on design. I think I started that last Monday. So it'll just cover everything up till today's lecture, till the end of today's lecture. So yeah. So if you don't have questions, that's it for